In this episode of KubeFM, I'm joined by Jorrick Stempher from Schuberg Phyllis. We dig into his article about scaling Kubernetes clusters across multiple environments and what it really takes to keep them secure and reliable. Jorrick explains how his team is using GitOps workflows to manage complex infrastructure, the guardrails they built for compliance, and the automation that keeps operations predictable as things grow. It's a practical look at running Kubernetes at enterprise scale without losing sight of developer speed or system safety. He would also like to give a shout out to some of his colleagues, but I'll let him do that because my Dutch is terrible. Dankjewel, and much respect to all the folks out there in Holland. Special thanks to TestCube for sponsoring today's episode. Are flaky tests slowing your Kubernetes deployments? TestCube powers continuous cloud-native testing directly inside your Kubernetes clusters. Seamlessly integrate your existing testing tools, scale effortlessly, and release software faster and safer than ever. Stop chasing bugs in production. Start preventing them with TestCube. Check it out at testcube.io. Now, let's get into the episode. Jorrick, welcome to KubeFM. For people who don't know you, can you just give us a quick overview about what you do and who you work for?
Yeah, so I'm Jorrick. I'm currently 22 years old. I'm still a student at Windesheim in Zwolle in the Netherlands, where I'll graduate the upcoming year, so next September or July, August, depends. I'm currently a junior software engineer at Apps for Tableau Infotopics, which is based in Hardenberg. I write software for Power BI and Tableau extensions, which is really cool. And I think that's about it. Yeah.
Good. And how did you get into cloud native?
Well, this project is what we're talking about today. Is actually the only time I've ever worked with anything cloud native. So it's only for school.
And how's that experience been? How did you get into it? What was the learning process like?
It was quite tough because, well, this project was the first time I ever did anything with Kubernetes. I had some Docker experience, but it was, not much. So it was actually really exciting because we had to run the project and also learn Kubernetes at the same time. So that was really fun.
And in terms of, learning Kubernetes, were there any resources, blogs, tutorials, anything like that you've checked out that's been helpful for you to learn?
Yeah, the project manager provided us with we call it a cursus. It was like so much hour of Kubernetes tools explained. I don't know what it's called. I tried to look it up, but I couldn't find it because it's on my old school mail. So I couldn't get into it. But it was really helpful for the entire project team because, of course, we worked with 7 other students.
Okay. And if you could go back in time and share one career tip, technical tip with your younger self, although I understand you're quite young, what would it be and why?
It would probably be that getting out of the comfort zone when it gets to projects and programming is totally cool, and I should do it more often.
Very good. Sound advice. Now, as part of our monthly content discovery, we found an article that you wrote titled Scaling Smarter, Predictive Node Management with Prometheus, Next.js, and Profit. So we want to dig into this a little bit more. Your team just completed a 3-part research series on Kubernetes scaling optimization. Can you give us an overview of what problem you were trying to solve and how this final piece fits into the bigger picture?
Yeah, so in the first week of the project, it's a school project, so it's 10 weeks, and you get an assignment, which is basically from a company or an individual, and you need to, do it as best as possible and follow certain school steps. So the task we were given by our supervisor, Ernst Bolt, was as following. He wanted us to create a scalable cluster in Kubernetes, which was hosted on Vultr. The cluster needed to be able to scale predictively, which is, of course, entirely different from scaling reactively, because when you scale reactive, you start scaling when the other nodes are already incredibly busy. So when your cluster is already overloaded, then you start scaling. And he wanted us to figure out a way to scale predictively. So predict whenever we need to scale up and make sure everything is done by the time we have the load we predicted. So we did 2 researches with basically a team of 8, including myself, and we were all software engineers. So we didn't have anything cloud. We'd never done anything with cloud native. Some of us had a bit of Docker experience, including myself, but not much. Never did anything with Kubernetes. So while running the project, doing the research, and making the service, the scaling service, we also needed to learn how Kubernetes worked. In the end, we did 2 researchers, cloud compute and optimization of scaling. Cloud compute focused on selecting correct virtual machine hardware config for our front-end and back-end to run on, and the automatization research focused on selecting a predictive model and researching node startup times. In the end, we made 3 medium blogs, 2 about researchers and 1 blog about the scaling service.
From your previous research, you discovered that a 1-to-1 vCPU to instance ratio was optimal for resource allocation. How did this finding influence the design of your scaling service?
Yeah, the finding directly shaped the design because it was a default scaling rule. And because in the research phase, we tested virtual machine hardware, and we found out that running multiple instances of a Next.js client as a front end on the same virtual CPU led to inefficient utilization. So basically, we had limited load capacity, random performance drops, and we found out that this was because Next.js doesn't really support multi-threading, because client, blah, 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 difficult. So when running 2 front-end instances on 1 CPU, we had a really low throughput. It was almost the same height as 1 instance. So we didn't bother. So we just said, okay, if we do 1 virtual CPU, we do 1 instance of a front end. And that's of course very important because we needed to know this before we started working on the scaling service.
You also researched node startup times in part 2 and found they averaged around 8 to 9 minutes. How did this timing constraint affect your prediction model's design?
Well, it only meant we needed to predict far enough into the future so that we had enough time to call the Vultr API, start the virtual machine, which, as you said, it took about 8.5 minutes because it was a first boot. So it needed to start up, install Debian or whatever we run on it. I don't know anymore. And it needed to be added to the cluster. And that took about 9 minutes. So we had to predict far enough into the future so that we could have enough time to start it up, edit, run the front end, back end, and be done in time.
Now let's dive into the architecture. You built a 5-component system to handle predictive scaling. Can you walk us through how these components work together?
Yeah, so we created 5 components. Combined, we called them the scaling service. And the components were a direct result of the 2 researchers and all the information we had discovered or were presented with during the project. The first component is Prometheus, which collects metrics from the entire cluster. So basically we say collect this, and collect this. And mostly CPU. That was, for us, was the most important. That then goes to the next component, which we called an adapter. It's basically a microservice built in Next.js. And it calls the Prometheus API and says, okay, man, I want you to provide me with this data. And it just collects everything. We then clean the data and send it to a Postgres database. Then we have the profit model, which runs at a set interval. So 10 minutes, an hour, 2 hours, 2 days, doesn't really matter. It queries all the saved data from the Postgres database, which was saved by the adapter. And it uses this to create a prediction 1 hour into the future. So we have CPU load, like this is what it's gonna do in an hour. So for each minute, I think we did a prediction for an hour. So 60 predictions, 60 CPU points. The results were then also saved into Postgres, and they were posted using a custom API to the 4th component, which we called the index calculation component, or just called ICC. The ICC gets a request from the prediction model, and then it starts calculating an index, which is an abstract number, a metric we created. We'll talk about that later. And it uses this index to determine whether to scale up, down, or don't scale at all. And then the 5th component is Grafana, and we query Postgres to display all the information we have on the web page. So the predictions are compared to the real time, and we have the real time only, prediction only, we have a MAPE, CPU load, all kind of stuff. Just a cool page where we can show, hey, look, it's working.
The Node Ranking Index, or NRI, seems to be a key innovation here. What exactly is this metric for people that may not be familiar with it, and why did you need to create it?
Yeah, well, we found out in, I think it was week 5, so we were halfway. we found out during the research we needed a unified metric to combine CPU, RAM, and request data. It was really essential because it allowed us to directly compare the resources. That wouldn't be possible otherwise, because CPU and RAM are completely different types of measurements. So without this random index, just a number, 1, 2.5, 3, it would have been really difficult to scale nodes up, down, cost and performance efficiently. It would have been way too difficult.
You chose Prophet over other prediction models like ARIMA, SARIMA, and Neural Prophet. What made Prophet the best choice for Kubernetes workload prediction?
Yeah, we needed a good balance between accuracy and training speed. And another key reason was the built-in seasonality, which was very important since the cluster load we were working with changes in predictable patterns throughout the day, week, months. So because it had all these things, it made it really easy to create reliable predictions for scaling decisions.
The Nest.js adapter does more than just pass data along. It validates metrics before storage. What kind of validation is needed, and why is this important for prediction accuracy?
Yeah, so when the adapter, the microservices call the API from Prometheus, it checks all the metrics before saving it to Postgres. And we found out this was very important using Grafana, because sometimes Prometheus gave us invalid data, like the CPU metric being 0 or 0 or anything else. And this could mess up predictions from Prophet. Probably not, because it's just a random number and one number doesn't really matter. But more importantly, it looked really ugly on Grafana. Like you had a really nice flowing line and then suddenly you had a spike going down or up, which was really random. So we just said, okay, if the metric is really weird, just don't save it and just go to the next. Just wait a minute.
Let's talk about the testing setup. You deployed everything on a dedicated managing node with taints and tolerations. Can you explain this approach and why it was necessary?
Yeah, so we discussed with the product owner Ernst, and he wanted the entire service to run on the same cluster, which we scale. So we needed to run it while we were adding and removing nodes. But what happens if we remove the wrong node where the entire service is on? Then nothing works anymore. So we had to use taints and tolerations to make sure that it couldn't accidentally remove itself, because, well, as I said, then it wouldn't work anymore.
All right. Your Grafana dashboard shows both real-time and predicted NRI values. How accurate were the predictions, and what was the typical MAPE you achieved?
Yeah, that's a good question. Well, as you can imagine, it truly depended on how much data the adapter saved in the database, because the more data we had, the better the predictions. Since we always tested in a testing environment with our own load generating script, it's hard to say how accurate the prediction would be in a real case scenario, because we just didn't have the time and or resources to really test this. Because it really takes a lot of time to create accurate forecasts. So our load generating script, it did fluctuate day to day and weekly. So on the weekend we had less, and Monday was a lot, and Tuesday was not a lot. And that switched each week. But it's not nearly as accurate as real-time traffic. The typical MAPE we achieved was below 9, which was quite good. And the lowest we ever got was 0.5. I only have screenshots left, which is a shame. I wanted to have some real data, but we don't have that anymore. I think it was around between 9 and 5.
Every few minutes, the Prophet model gets retrained on new data. How did you determine this retraining frequency, and what happens during the retraining period?
Yeah, so as I said, we only had 10 weeks. And that was including building a front end, back end, doing the research, and building the service. So we didn't really have a lot of time to train Prophet. So what we did, we rushed through the first few weeks, and then we trained Prophet during the Christmas vacation, which was 2 weeks, which don't include in the 10 weeks project. So it had 2 weeks to train. So therefore we created a script. It is basically a small DDoSer. So it just sends a lot of packets, which fluctuate to the day. And then by creating enough of a pattern, we could train it. The retraining period was, I think we trained it every 15 minutes. And basically, during retraining, it queried all the data and looked at it and, okay, well, if I look back at Tuesday last week, what does it do, and what do I have today? Does it look the same? Okay, then I think it's going to do this. And most of the time, it was really accurate. We ended up deleting the entire training data from the Christmas vacation because we messed something up. And I think we trained it quite accurately in 2 or 3 days. But that also depends on our script, what it does.
The index calculation component makes the actual scaling dimensions based on the NRI. What logic does it use to determine when to add or remove nodes?
Yeah, so I think the ITC was the most complicated component of them all, and because the process itself is quite complicated. Basically, it retrieves, when it gets a call from Prophet, like, hey, here's my prediction, good luck. It retrieves all the running nodes on the cluster. So it knows, okay, this is what's running now. This is the power I have. And it uses that information to create one node ranking index. So one simple number, let's say 3. The next step is to calculate what the necessary index is. So therefore it uses the Prophet prediction, and it saves the highest number it goes to in the coming 15 minutes. Then using that value, it calculates a new index, and it compares the one it currently has and the one it has in 15 minutes. Then it uses a recursive calculation to find the best combination of node plans needed to reach the required capacity, because basically the index directly translates into capacity. And this way we didn't create any duplications or weird combinations, and we also made sure that it removed the nodes which we had to pay for the soonest, because you pay for each node a virtual machine an hour. So we first removed the first ones, and it all did this at the same time. It was really, really cool process, really difficult. And after all of this is done, it just calls the Vultr API and says, okay, we're going to add one node with 4 virtual CPUs, and I want to remove this one with 2 virtual CPUs. That's basically it.
Okay. And then during testing, you used a load testing script to simulate realistic server usage. How did you ensure your simulated load actually represented real world patterns?
Yeah, so we used virtual users to generate loads. Each virtual user makes a certain number of requests depending on how many endpoints we have. So the API we created had, for example, 5 endpoints, and each virtual user sent 1 request to each endpoint every second. Something we had to keep in mind were startup times, because when we started sending load to the client or API services, the load immediately went over the threshold we set, which was a 95% successful request within a specific time limit. This happened because we went from 0 load to, let's say, 5,000 requests per second, which the CPU couldn't handle, and it failed the request, and the test ended immediately because it was all automated. So what we did is we added a ramp-up time of, let's say, 5 seconds. Doesn't really matter as long as it's always the same during each test. And this helped us test the nodes properly, because many crashed instantly, and they worked fine with the ramp-up. Of course, it's also really unrealistic to go from nothing to 10,000, 15,000 requests per second in an instant. So we did that. The use case from the client API which run on the cluster was a school-related project. So the idea was, okay, during the weekends, not a lot of students would use the platform because it's weekend. It's probably busy on Monday and on Thursday because those are busy quality days at wintertime. So we calculated that into the load generating script. A fun fact for this is the entire project was run at school. So we had a classroom with a lot of monitors and the team. And one laptop couldn't generate enough load to hit the threshold at a moment. So we did test, I think, 8, 9, 10, 12 different virtual machine hardware combinations. And one laptop just couldn't send enough load. It couldn't send enough packets because the school Wi-Fi limited the amount of package we could send per device. So I think we had 3 or 4 laptops running the script at the same time to try and take down the our own virtual machine, which was done in advance, and we checked this with school and with Vultr, and it was all fine. So before you think we're trying to do it down our school systems, we didn't. Would have been fun.
That's I say normally that is the case. That's exactly what people are trying to do.
Yeah.
I'm glad you chose the path less traveled. That's good.
Yeah.
So looking at your results, you achieved accurate predictions, efficient resource usage, and dynamic scaling. Were there any unexpected findings or challenges you encountered during implementation?
Yeah, a lot, which was basically all made by the fact that we were all software engineers. We didn't have anything. We didn't know about cloud native before we started with this project. So that for us, that made it really difficult to understand what Ernst, our product owner, what he wanted. So we had a lot of moments where we're like, oh damn, shit. I think Vultr already offers this entire system, but that was not a predictive system. It was reactive. That was one of the issues. Another issue was that we only had 10 weeks to do everything. So we had to learn Kubernetes, build a content management system. That's the client and API we made. It was a small YouTube Studio-like system with a small client and a small API. We had to make this because otherwise we wouldn't have anything to test. And we, of course, still had school. So the project was run next to classes, which we had on Monday. So we only had 4 days a week to work. Luckily, we had a great team. Every one of us knew each other quite well before we started. We were all on the same teaching assistant team, so that was really nice. And it made the process really enjoyable. Another issue we had was all of the tools we used next to Kubernetes, like Helm, Prometheus, and Grafana, were completely new to us. So we had a really tight timeline, and we had a lot of stressful moments, but we also had a lot of good moments. And I think the best moment we had was when we thought of the NRI and we really had a working calculation component. We're like, yes. I think we celebrated with cake or ice or something.
Very good, as you should. So for teams that are out there who are looking to implement similar predictive scaling solutions, what advice would you give based on your experience? Like, what would you do differently if you had to start over?
Yeah, I think I would select a team full of Kubernetes masters, so people actually know what Kubernetes is capable of, because we figured it out in a few weeks, and I think we did quite a good job, but it would make the entire process much easier, and you could probably do more in 10 weeks. Also, do your research. We worked on ours for 2 to 3 weeks, which was really a lot for a 10-week project. But if we skipped over some parts of the research or just cut some corners, I think the scaling service would have never become so accurate and robust as it did in the end. To be honest, I can't really say what I would do if I were to do the project over again. As team lead, I was really happy with the entire process we had. And the final project was really good. I think we got like a 8.5, which was quite high. We were quite disappointed, but it was a good grade. And we're really happy. So I don't think I would do anything different. But that's difficult to say because now I know how it works. So
fair enough. And this was this was clearly a team effort with 8 developers working together. Can you tell us about the collaboration and also give a shout out, if you like to your colleagues and mentors who made this project possible?
yeah, so the project ran during the second period of the Quality in Software Development semester at the HBO ICT Bachelor program at Windesheim in Zwolle, which is a great semester for anyone who wants to do programming. We worked on it with a team of 8 devs, including myself. I really want to mention their names because they are awesome. The names are, look them up on LinkedIn, Jasper van Willigen, Martijn Schumann, Ties Greven, Teun van der Klei, Jeroen Terpstra, Bas Plat, and Stefan Lond. All Dutch names, really difficult. And our project manager, Ernst Bolt, he came up with the project. He came up with the idea of the predictive scaling, and he oversaw the entire thing. So he paid for Vultr, and we really had a great time with him. It was awesome. And we also had a lot of support from Windesheim. Our mentor from school was Sean Brouwers. He helped us manage the entire process into building something that's cool, good, great for us. So it was really great. I really had a great time during the project. I think the combination of the project and all of the awesome people I did, it was probably the most epic thing I've ever done in coding.
Very cool. Well, that being said, what's next for you? What's your next challenge? What's your next project? What are you going to be doing?
Yeah, so the next semester I'm doing an internship at Infotopics at Fortebleau. And after that, I'm graduating, and I'll see where the ship's trends. I don't know. We'll see.
Very good. That works. And if people want to get in touch with you, what's the best way to do so?
Yeah, you can contact me on LinkedIn. I think there's a link somewhere after the podcast uploaded. So contact me. It's just my full name. You can find it. Not a lot of people have my name.
Okay, yeah, that's true. You're the first Jorrick that we've had on KubeFM.
Awesome.
And possibly the only one. It's like you said, it's a unique name. Very nice chatting with you. Great learning from your experience. Look forward to seeing what you're doing next. Embracing the challenges, the teamwork, the collaborative aspect. Really nice to see people that are using Kubernetes for the first time and not dying in the process. So congratulations for all your hard work, and look forward to speaking to you soon.
Thank you. It was great being here. Thank you.